Uh, Good morning, everyone. Uh, I want to welcome you to my lecture today, and you are welcome on board. To the new summer semester. Uh, my name is Kazim. I hold a PhD in mathematical statistics, and of course, I'm going to say I started my teaching career in Nigeria because I'm originally from Nigeria. I started teaching at this level in 2012, and I think I taught for more than 5 years before relocating to United States. And this is my fifth year at the University of Minnesota. Apart from being a professor at the department, I'm also assistant director of undergraduate studies at the School of Statistics, University of Minnesota. Um, I'm going to say that I'm going to be the lecturer in this course, in charge of this course. This course is applied, and I can assure you, um, I'm going to make the course very interesting to you because I'm going to be relating whatever we do to real life or practical situation. I cherish, getting feedback from students because I'll be able to know whether you understand the message I'm passing across if I can hear from you. So I cherish getting feedback. Then I also award extra credit, for those who answer my question in class. You can use your extra credit towards assignment. You can use it on midtime. You can even use your extra credit on the final exam. So when you answer my question correctly in class, of course and you can be accumulating your points. Okay, so I think I've done that for so many years. Of course, my office hour, I'm gonna be having my office hour Mondays, Wednesdays, Thursdays, uh 11 to 12. I'm gonna have that both in person on online for those who actually live far away. Of course, I'm not gonna start my office hour today. I'm gonna start on Wednesday, but as you can see, it's gonna be Mondays, Wednesdays, and Thursdays. Okay. In this course, there's going to be a lab session, and I need you to take the attendance seriously of the lab section, because in the lab, you're basically going to be work on how to implement statistical analysis using R codes. I can assure you R is, this R software is very, very easy to learn, because whenever I give assignment, I expect that you use the knowledge of the lab. Okay, so and if you have issue in the lab, this I need you to tell me because I'm in charge of, because so that I can actually call my TA to order. Okay, so please let me know, what is going on. Okay, so that's my phone number. Of course, I pick call when students call me. Okay, and if you find yourself struggling in my class, please make sure you reach out to me, and whatever we discuss will be treated with absolute degree of confidentiality. Okay, you can trust me. Okay. uh is there anyone who have trouble time getting the struggling getting the way I talk? Is there anyone who doesn't understand my English or my accent? Is there anyone? Like I said, do not hide your feelings. Okay. Even though I was not born in the United States, but I'm actually going to try to make sure I communicate. Okay. But in the process, maybe you see that I'm talking slowly or talking so fast, please let me know because I want to be statistical in my talking. Okay, so the goal today is just to refresh your memory of the basic statistical concept because you need that memory for you to be able to understand what I'm going to be passing across. Then we also need to get yourself familiar with notations. Let me tell you this. It is not as if statistics is difficult. It is not as if anything mathematical related is this if difficult. Uh, I think what students normally find difficult is understanding of notations, symbols. Okay, so I'm actually gonna make sure I relate every notation, every symbols to real life, practical situation. Okay, so the moment you don't understand a particular notation, please make sure you ask me. Does that make sense? Okay, so like I said, today's work is more or less like you know review basic statistical concept. Okay, that will enable you to understand what we want to do in this course. Okay, now we want to talk about statistical concept. You know, let me tell you this. Before I go into applying statistical concept, I'll first tell you this. You know, the existence of physical world, existence of physical world or reality is independent. Is independent of human knowledge. Okay, the existence of the physical world is independent of human knowledge. And if we want to understand the world we live in, we need knowledge. But where does the knowledge come from? The knowledge actually comes from the information that we got, because it is the information that we translate into knowledge. But let me tell you this: where do we get our information from? Now, the information will actually come from data. There's a difference between the two. There's a difference between data and information. Okay? Now, let me tell you this. We want an information, and that information will translate into knowledge, and the information will come from data. Now, this is the situation. If I want to understand the environment that I live in, if I want to understand the world, I need information. Where will I get the information? I will go to the population. Okay? I will go to the population to get the information. But you know what? I don't have resources to study the entire elements in the population because we're limited by budget. Because of that, from the population, we're going to take a sample. Okay, we're going to take a sample, right? The sample of data. Okay, and let me now tell you, when we take a sample and we collect our data, we don't get information. The information is not available immediately. Something needs to be done on data to be able to extract the information. I'm going to say this again. We need knowledge to understand the world. And it is the information that we translate into knowledge. Information comes from data. The data that we collect, this information that comes from the data, it is not readily available. Something needs to be done to data before we can have access to the information. You know what needs to be done to data? We need to be able to apply model, statistical model. The statistical model will help us to extract the information in the data, because the information that we have in the data, they are not readily available. Something needs to be done. But let me now tell you this. The amount of information you get on the data depends on whether you are using appropriate statistical model. It is not all statistical models that are appropriate. And that's why in this course, you know what we're going to do? How can we actually apply appropriate statistical model to a given problem? Because, and let me also tell you this. When you use model or to analyze data to get information, you can never get 100% of the information in the data. There's always going to be information loss. I'm going to say that again. There's always when you use the best model cannot extract all information in the data. There will be information loss. And because of that, that is the reason why we said model is just model is an approximate reality. We want to use model to capture reality, but model cannot give us exact reality. Because you know why model cannot give us exact reality? Because there's always going to be loss of information, which we call the loss of information. The loss of information is what we call the error. Every statistical model has error. That's how it says to you. Then what do we do in statistics then? How we can minimize our error. Because we acknowledge the fact that there's always going to be information loss. We don't want a lot of information to be lost. But the only way you can actually minimize that now depends on the model you are using. We got different statistical models in this course. Okay, your ability to be able to apply an appropriate statistical model to a given situation will actually lead to a drastic reduction in the error. We always want to bring our error under control. Okay, now we are back at statistical concept now. In statistics, we believed what we want to capture. Why is it that we are applying model on data? We are applying model on data because we want to get information, and the moment we get information will translate into knowledge. Then when we have knowledge, then we understand the world. Okay, but let me tell you, the world we live in is a random process. Why is it random? Because there's a variations in the world. We have there exists more than one state of nature. And that is the reason why we get worried. If there's only one state of nature in the world, then there's nothing to worry about. We get worried because of the fact that there's variations. And that is the reason why, what are we trying to do? We want to, when we say random variable, we're trying to quantify the outcome of a random process. When we talk about random process, a process that can lead to any result. Nobody can we may not be able to predict exactly what will happen because it's a random process. So how can we quantify that? Okay, then the idea of statistics can actually be used. Of course, the moment you hear variable, right? What do I mean by variable? Let me even give you the definition. When I say variable, because right now I'm talking about random variable. Okay, when I say variable, so what do I mean by variable? A variable is anything that is liable to change. Okay, anything that is liable to change. Okay, anything that is liable to change. Okay, anything, okay, that is liable to change. Okay, we live in a world where maybe my philosophy yesterday may be different from my philosophy today. Maybe the way I think about somebody yesterday may be different from the way I'm thinking about the person today. It's because of the world we live in. Okay, anything that's liable to change is what we call variable. But this time around, we're talking about random variable. Okay, now in this course, when you hear random variable, we're going to be using a notation, an uppercase X, Y, Z, W. It's going to be an uppercase, not a lowercase. Does that make sense? So please let us pay attention. Now, in this course, when I'm talking about an uppercase X and a lowercase x, there's a difference between the two. Okay, the uppercase S is random variable. The lowercase is a particular value of the random variable. And that's why I'm gonna give you this as an experiment. Let me tell you something. Uh, in a stochastic world, we perform experiments. It is not until you are in your physics lab or in your chemistry lab or in your biology lab, life itself is an experiment. The way you are, the way you are sitting down today, like, okay, uh, you are experimenting because you have a target. Your target, even though you have certain thing in mind that, oh, I'm gonna understand this course and I'm gonna pass this course. Okay, which means when you are writing an exam, when you are preparing for an exam, you are experimenting. Okay, now a lowercase s is a realized value. If I perform experiment with a die, of course there are 6 numbers in a die: 1, 2, 3, 4, 5, 6. Then the random variable can be 1, 2, 3, 4, 5, and 6. But when I say a lowercase x, I'm referring to a particular value. Does that make sense to you now? Okay. Now, take a look at that. Random variable can take on different values. I'm actually going to give an example here. If my car breaks down, I'm able to trace it to, it's either in the sample space. Okay, there are 3 possibilities in my sample space of what could be the reason why my car breaks down. It could be due to electrical. It could be due to mechanical. It could be due to misuse. These are 3 possible reasons why my car breaks down. Now, if I now want to talk about the state space, the state space now, in terms of cost, if my car break down due to electrical, how much on average did I normally spend? Oh, maybe $50. Mechanical, maybe 80. Misuse, maybe 300. These guys are random variable. The random variable is assigning figures to elements in the sample space. These are elements, right? There's a sample space here. There's a sample space. A sample space is different from a state space. A sample space has elements. These are elements. Okay. Now, when I have figures, what am I doing? I'm assigning numerical values to the elements in the sample space. Okay, so these are figures now. So which means I spend between what? I spend between $50 and $300. Okay, which is going to serve as the range of my random variable. So which means if I want to define my x, my uppercase s, my uppercase s is basically 50, 80, 300. But if I want to talk about a lowercase, maybe I'm interested in just 50 or less than 80 and so on like that. That's exactly what I'm trying to say there. Now, take a look at what I'm trying to talk about now. where if y represent the weight of a student, when I say the weight of a student, of course I expect different students to have different weights. Okay, y and an uppercase y, I may want to find a probability. What is the probability that the weight of a student will be less than 140? Take a look at that. Okay, so less than 140, that 140 is basically a realized value. Does that make sense to everyone? Like I said, statistics is very easy when you are able to interpret, when you're able to relate. Okay, now this is a quiz one, just a general. This variable can only take on the final values, yes or no. Now let me tell you this: when we talk about random variable, we can have a discrete random variable, we can have a continuous random variable. When I talk about discrete random variables, I'm referring to those variables that can be expressed as whole numbers. Number of students in this class is discrete. Numbers of goals in a match is discrete. Does that make sense to you now? But when it comes to expressing, value in an interval, then I have a continuous. Please take note of that. Okay, now discrete variable can only take on a finite numbers of value. It is false because we can have some discrete numbers that can also, we can have it in a way where there's no limit. Okay, now this is an example of the different, when we want to look at the difference between discrete and continuous. Like I said, the year a student in this course was born, the numbers of ant born tomorrow, the possible value that can be listed, and for continuous, we're talking about percentage or something in the interval and so on like that. Now, we want to come to probability distribution. What do we mean by that? We need the idea of probability in statistics. Why do we need the idea of probability in statistics? Is because in statistics, we take a sample, right? Instead of the whole population. And the idea of probability will be applied for us to make a generalization. Because when you take a sample, we need to ensure that everybody in the population has equal chance of being selected. What is that? Randomness. You are using the principle of randomization. And let me tell you, when you are using principle of randomization, then you are already applying probability knowledge. There's no difference between randomization and probability. Okay, now when we talk about probability distributions, what does it mean? Oh, when I have data set, the idea of probability distribution will enable us to know what is the possible values the random variable can have and what is their corresponding probability. It's just like I take a measurement now. Okay. Now the idea of probability distribution is going to tell me what is the possible values I can have. Like the other time I was, okay, like here now, the possible values I have is from 50 to 300. Not only that, how many times? Maybe I now continue, maybe I now do this. Maybe I put a probability space and I said, I put this, I put this, and I put this. You know what I mean? This guy means, 50% of the time when my car broke down due to electrical, I spent $50. See that? Look at that. 30% of the time when my car break down due to mechanical issue, I spend $80. And 20% of the time, now with this now, I have a probability distribution. What we mean by probability distribution is that will enable us to know what is the possible values the random variable can have. And not only that, the frequency, like what is the number of times a particular random variable occur. The numbers of times this guy occur, 50%. The numbers of times this guy occur, 30%. Now, do you now understand what we mean by probability distribution? I remember when we were in school and they mentioned probability distribution, so people will be scary and they will be running. Oh my God, that's too huge. No. What it means is just like, what is the possible values? The possible values will be displayed in the horizontal axis, while the frequency, okay, will be displayed on the vertical. An example of a chart in statistics that will show you the probability distribution is histogram. Has anybody heard about histogram before? Okay, good job. Now, two important measures of distribution. Oh, go ahead. Yeah, what is the difference between them, right? Oh, okay. The difference is just like the state space is just going to talk about possible elements, not figures, elements, right? Elements in the samples, elements in this, like possibility. I told you the other time that, oh, when my car breaks down, maybe it could be due to this. If I can only trace it to just these three, this is what we call sample space. But when I say state space now, it's like assigning figures, numerical values. Now, the numerical values I'm assigning now, I'm assigning that in terms of cost. So I need to define that. Oh, these are just the amount of money I spend to repair my car, due to certain reason. Does that make sense now? And this guy now is looking like a set in mathematics. Look at the difference between mathematics and statistics now. And that's why I used to say, statistics is a mathematics that makes sense. Okay. Now, you understand what distribution means? That's a very good question. Now we have two important measures of a distribution. We find ourselves in a world that is full of variations. You know what important thing we're looking for? Average. We only want to know the mean. Okay? We're interested in that guy. Expected value of S, which is the same thing as the average. In a stochastic world, in a probabilistic space, you don't get the exact thing. We are okay with the average. Does that make sense to you now, right? When we're making our prediction will be based on average. Now, the measures is, like I said, the two important measures is the mean and the variance. Okay, some of you were wondering, mean, variance. Oh, when I get mean, since mean is an average, the mean, an average is like this guy. We got a lot of people here, right? And this guy is representing them in the Congress. This is a city, right? This is a city, right? And this guy is representing them in the Congress. Okay, this guy is like the average. How do we know this guy is representing them well? That will now depend on the closeness. Because if you want to represent your consistency, you must not be far away from your consistency. If you have a senator or you have any congressman or woman that doesn't visit the consistency regularly, that is not representing them because he doesn't know what they are talking about. That is the same thing as the mean. How do I know mean is a good representative? Then I need to look at the variance. Does that make sense to you now? Okay, the variance will tell us how reliable is the mean. How reliable is your average? That's what the variance will tell us. And that's why those two become important measures in statistics when it comes to distribution. When you are learning statistics, I will need you to like follow whatever you learn with a practical mind. The moment you follow that with a practical mind, of course, you're basically going to be fine. Oh, I find the mean. Because take a look at this. If I have, okay, I want to find the average here. If I want to find the average here, the fact remain, let's say for instance, I don't have the probability. If this occur, okay, if they have the same weight, I'm just going to do this plus this divided by 3. Because I'm assuming the same weight. Each of them has equal probability, 1/3. So which means when you are calculating your mean, you are assuming equal weight. Does that make sense? Now, when you find the mean, if you add this to this to this and you divide by 3, the number you are going to get will be different from all this. You know that, right? How do we know the number you got is a good representative? The same way you're going to know whether this congressman or woman is a good representative, because where does it come from? From this place, right? Okay, and they maybe the election process, and it's okay, we choose you. How do we know we are representing us? Then we look at how far apart is the mean from the respective observation. We want to measure how far apart is the mean, because if they are not far, it will be representing them. But if it's too far away, which means if it is too far away, the variance will be large. If it is very close, the variance will be small. Does that make sense to you now? Start is easy. Now, take a look at that. Okay, so we have notations. You know, when we take a look at that, mu, we call that population mean, but we don't use everybody in the population. We take a sample, right? Okay, now when you, and let me tell you this, when there's an election in a particular country, it is not everybody in the country that will vote. So sample of the country we vote, okay, which means the average that you're going to have is going to be called a sample average. Then if you want to calculate the variance, even though we're looking for sigma squared, the sigma squared is population variance, but we can't get population variance unless you study everybody in the population. What we normally end up getting is a sample variance. Does that make sense? And how do we compute the sample variance? That is the formula. That makes sense, right? Okay. Now, there's something I want to show you now. When I'm working with data set in statistics, what we basically want to do, because we use the idea of probability in statistics, you know, for us to be able to generalize, okay, the result that we got from the sample on the entire population, okay, we need to, for of us, investigate what is the distribution of our data set. I'm going to say that again. We need, because we need to know, is the distribution of our data set normal or not? If the distribution of our data set is normal, what are we going to do? We can use the formula here to get the mean. We can use the formula there to get the variance, which means we are assuming equal what? Equal weight. And at times, I gave you something here the other time. Do they have equal weights here? No. Situation where there's no equal weight, it means the distribution may not be normal, because we have approach in statistics that we can use when our data set follow normal distribution, and we have approach in statistics that we can use when our data set do not follow normal distribution. So which means when you are working with your data set, how do you know the probability distribution? Now that's what we want to show you now. Now, if you take a look at this, a normal shape, the mu is at the center, okay? Now, when you move away from the center, okay, you know, the deviation from the center can be measured using the number of standard deviation. Now, how do I know if the data set that I'm working on is normal? If 68% of the data set fall within one standard deviation, and 95% of the data set fall within two standard deviation. When I say within two standard deviation, it means two standard deviation below the mean or two standard deviation above the mean, the other area. And if the 99.7% of the observations lie between three standard deviation, then I can conclude the data set that I'm working with is normally distributed. Then if it is normally distributed, then I can go back and use and compute the two important measures. Otherwise, I cannot do that. You know, let me say something. It's not as if our models are failing us. Our models are not failing us. but we are the one that we're not doing the right thing. So now take a look at that. Okay, now this is using the empirical word, okay, from the empirical rule. And let me tell you, some of the scenarios in the real world follow normal distribution. Particularly if you want to talk about income distribution, they're going to say, oh, we have a middle class, right? Okay, below the middle class and above the middle class. Now, I want to take it to notation now. Okay, now we are now working on normal distribution. Okay, now when you take a look at, uh, we want to talk about sampling distribution of X bar. What is the meaning? I'm going to tell you the meaning now. If I'm interested in the average, in the annual household, the average annual household income in the United States, and these are researchers. This guy go into United States population, take a sample, and compute the average annual household income. This guy did the same. This guy did the same. This guy did the same. They all do the same. They will get different results. Why are they getting different results? Because the participants selected by this guy is different from the one selected by this guy, and that is the reason why different researchers at times when they are working on the same study, they got different results. There is sampling variability. Now, we now have this guy got average, 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 average. What happened to average now? Averages now become random variable because the averages varies. Now, but let me tell you this. If I have average, the first average, the second average, and so on like that, okay? So if I have the first average, the second average, the third average, until I get to maybe I have 1,000 researchers, 1,000 average. All these averages now, because they varies, they become random variables. And when they become random variable, then we now try to understand what is the range of the values and what is the probability distribution in terms of what is the numbers of time a particular value occur. When I'm doing that, then I'm doing sampling distribution. Like here now, we're talking about X bar. Let me use X bar and let me use X so that I'm not going to convince you. X bar 1, X bar 2, until you get to X bar 1,000. Okay, now this is what happened. When you go into, when this guy go into the population, this guy choose a sample N1, this guy choose a sample N2. Maybe they even selected the same values. This maybe they observed 20, 20, 20 or 2, doesn't matter, but they got different results, right? Okay, if they got different results, let's focus on this guy. On this guy go into the population. X1 is the response that he got from the first person. X2 until we get to XN. Like I said, maybe he choose 20. Then what did he do to all this? He added their opinion, right? Maybe he say, okay, oh, how are you doing? What is your average salary? This person said 20,000, and this person said maybe 25,000. They're going to say different thing, right? And this guy now find how did they find the X bar is use summation XI over N, right? It got that very mean, right? Now the belief is that the X1, X2 up to Xn follow a normal distribution with a mean of mu, the variance sigma squared. Now each of the investigator have they compute their mean, but right now there's a variation in the averages, and averages now become random variable. Then we can now say X bar also follow normal We mu this, but the variance is going to be sigma square over n. So what I'm trying to say is that if x follow normal with the mu this, the variance is sigma squared. There's a difference between this and this guy. Even though they have the same mean, but the variance is different. But the variance of this guy is going to be the same as this guy only if n equal to 1. Is it possible that we interview only one person? No. And that is why we normally go with this guy. Because the moment n is greater than 1, the variance will be smaller than this guy. And that justifies the use of sampling distribution. Does that make sense? Okay. Now, the central limit theorem we now apply. This is the situation. We want a situation where the distribution of this guy we follow normal distribution, right? And the only way it can follow normal distribution, even though the population we're choosing from is non-normal, okay? If the population we're choosing from is non-normal, let me tell you this. When you are conducting a study, okay? We don't go into population several times. We only go once. But what we justify going once is when your sample size is at least 30. When your sample size is at least 30, then the sampling distribution of this will be normal. So according to the central limit theorem, okay, provided your sample size is sufficiently large. How large is this large? It has to be at least 30. When it is at least 30, then the distribution of the X bar will follow normal distribution, because in statistics, it is only when the distribution of X bar follow normal distribution that we can get something reasonable. So what is it trying to tell us? Encouraging us to take large sample. This is the reason why at times a court will start a case and they may not decide until 20 years. What do you think they are doing? They're taking more sample. People will think that, oh, they are delaying. No, it's not like that, because they don't just conclude on a case like that. They don't want to commit error. Okay, and that is why. So it means they are taking, large sample. Okay, now apart from having a normal distribution, we have another form of distribution that we call T distribution. Okay, the T distribution we're going to be talking about, we're no longer going to be talking about, we're going to be focusing on the degree of freedom. V that you see means degree of freedom. And what do we mean by, what is it? When I say V, degree of freedom, the degree of freedom is the number of sample size minus 1. It means we are not going to guarantee freedom to all the sample size. Okay, we can only allow n minus 1. Like if I have 40, okay, all the 40 cannot be free. We only going to allow only 39 to be free. So that's why. But let me tell you, when sample size increases, this particular distribution approaches normal distribution. So in statistical analysis, we also make use of this, because in the regression that we're going to be doing, you're going to see us talking about using the normal distribution, using the T distribution. Okay, so what I'm walking you through now is just, and that is a person, who actually developed that. Okay, now how does T distribution relate to normal distribution? I want you to take a look at this. They are related. I said if x1 is a random variable that follow normal distribution, if then the x bar minus mu divided by s is the sample standard deviation divided by square root of n follows T distribution. Okay, and not only that, I also said if x1, x2 up to Sn is a random sample from any distribution, then x bar minus mu will always follow T distribution when n is large. This is just a condition, okay, under which that will happen. Now, I want to talk about parameters. Let me tell you something. Parameter is a population characteristic value that we seek to determine. Anything that we want to know that we don't know right now is what we call parameter. You may want to know what is the average allowance, or what is the average annual household income in the United States, or what is the proportion of Americans who approve the job the president is doing. That's a parameter. So parameter could be mean, it could be variance, it could be proportion, anything that we want to know that we don't know. Okay, so the values that define a distribution in a family is called parameter. But let me tell you something. And we also they are always unknown. Now, when we're talking about distributions, there are two parameters in a normal distribution, mu and sigma squared. For T distribution, the parameter is V. What does V represent? Degree of freedom. So if I want to use a normal distribution, I need information about the mean and variance. If I want to use a T distribution, I need information about the degree of freedom, V. Okay, that become parameters. I just wanted to take note of that. Okay, now, do parameters have probability distribution? Now, let me tell you this. When you want to argue from frequencies point of view, parameters does not have a probability distribution. But if I want to argue from Bayesian point of view, of course, parameters have a probability distribution. But from what I'm actually going to be teaching in this class, assumption is that even though our parameters, they are unknown, but they are fixed. They are not subject to variation. Does that make sense? I'm also going to tell you when they are subject to variation. Okay, I think what I'm going to do at this time is to stop at this point, and I'm basically going to continue from this review tomorrow. I need someone to ask me question based on what I've reviewed today. Like I said, I'm basically going to continue from this tomorrow. Any question on this review? Is there anyone who want to ask question? Like I said, you pay for the service and you deserve to be served better. Okay, yeah, go ahead. That's a very good question. You know, the notation I've just shown you now. I said, okay, let my V represent degree of freedom. If you also use DF, I'm okay. I'm okay. You know, provided, in fact, if you use M, provided you now define that your M to be the degree of freedom, I'm fine. Yeah, that's a good question. Any other question? Okay. Uh, Make sure you. I think I really appreciate you coming to my class today. And if there's any, maybe I know some students may want to ask questions, but they don't want to ask right now. You can send me a message, okay? Or you visit my office hour. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone. You're welcome.